We're on. Okay, so we are today's Wednesday, and if you have started reading chapter 3, you'll notice that they start chapter 3 a little differently than I did yesterday. Jonah is questioning, hey, if he has time, if you have time. There's no pressure, Jonah, but his dad has something to do with mass spectrometers, and so that's what they show in the first few pages. So he thought he'd learn a little bit more about it, and he would actually give a presentation about it, and then we can talk about the first 3 or 4 pages in. See that? So anyway, and like I said, if you can't do it tomorrow, just say, I know I can do it Monday. So just let me know. I don't know how much is on your plate right now. Okay. Okay, so what else? So we are, this chapter here is, we should be able to move at a pretty good pace through this one. I certainly would be willing to help any of you if you said, I'm just a little bit behind, or, so the first part of the chapter, if you read it, has to do with the mass spectrometer, but we'll get to that. And it talks about where we get these decimal numbers from, and how can we be a little more sure about the mass, the average mass of an atom. Okay, but then they go into classifying and balancing equations. Now that's a skill that I think everybody should have. Many of you will take chemistry probably next year in college. If you have any kind of a science, medicine, you probably will take it. And this is a skill I know you'll be using. Of course, what if you can't write formulas? If you can't write formulas, you're going to have trouble balancing equations because you have the wrong formula. Is that right? So that's why I kept telling you that being able to write formulas is very important. Okay, so then we learn how. I'm going to show you some little tricks again, same ones I did before. But show you some tricks. How do you balance an equation? Make it not so hard. Some of them are hard. Some of them are just hard. But we have some tricks that we can make them not so hard. But then after that, I think one of the pinnacles in chemistry is stoichiometry. And that's where you actually use mathematics with the balance equation, and you're able to do some pretty neat stuff. I don't know if you remember this, but there were 2 kinds of stoichiometry. The easier one, where I give you so many grams of that, and you figure out how many grams of this will react with and how many grams of product. Those are the easier ones. The harder ones were where I give you the amount of grams of both reactants, and I say, now how much product is going to be made. And I don't know if you remember the peanut butter and jelly analogy, but remember the limiting reactant things? We need to do that. I feel pretty certain that if you were at the college and you had this under your belt, you'd feel pretty good. You'd feel pretty good, certainly in the first month of school. Depends on where you go. Some professors say, well, I'm sure they know stoichiometry. Let's go. I'm sure they know measurement, and they're going to do a lot of things like that. I'm sure they know how to write formulas. There are a lot of kids that don't. A lot of smart kids that don't. So anyway, I'd like you to have those skills so you're going to be pretty good. Okay, well, we had the last thing we looked at was this sheet here, and this is just a little more detail than we did before. And there we go. And I think we were down here, and we were talking about different kinds of decomposition. And EJ later came up to me, and he said he's taking an AP Bio. What is it called? AP Bio. And he's really enjoying the link. He's actually seeing much more chemistry, how the link between chemistry and biology is really there. And he said, well, we're doing a thing called dehydration synthesis. Okay, and we were talking about that yesterday after class, where you take something like, this might be a glucose, or this might be a glucose, or that might be glucose and fructose, but you take these 2 compounds, and they already have all their bonds. They don't want to form a bond with each other, but God made enzymes in a living cell, that almost every chemical reaction in the cell has some kind of enzyme. It's catalyzed. It's a catalyst, okay? And so there's a catalyst that actually is able to rip an OH off of this guy and an H off of this one. And we're trying to draw it up here. So if you were to rip an OH off of one, then that carbon wouldn't form another bond. And we have this later when we do a whole unit on organic. And then rip an H off of this one, that wants to form a bond. Then the 2 sugars can form a bond with each other. And all of a sudden, you took two simple sugars and made something more complex, and that's called synthesis, right? You were building something bigger. And because you took water away, it was called dehydration synthesis. Some books actually call that a condensation synthesis. Did yours use dehydration? Yeah. Okay. And same thing here. You can synthesize more than one. That's a simple way of doing it. But you can take three things and make two things. You know, as long as you're building up something bigger, it can be called synthesis. Yes?
Couldn't that also be kind of considered like a massive single replacement kind of thing?
The one I talked about with the sugars?
Yeah.
I say no there because here I didn't replace anything. I took an OH off of you and an H off of you. I actually ripped it off of you. I didn't put something else back in its place. Whereas if we get into replacement, you'll see where I kicked you out and took your place. See that? Or double replacement, I kicked you out. No, I kicked you out. They actually are replacing the thing that was in there. So I guess I wouldn't call those any kind of replacement.
Are you not removing the water, you're just changing it into something?
One more time.
Are you not removing the water, you're just changing it?
I am removing it, but I'm not replacing it. So like replacement means I'm kicking you out and I'm taking your place. So and so we have to, even though this is a general idea, what if I took something like this and broke it down and it formed two things? Would that still not be decomposition? Another thing that's kind of neat about decomposition, notice that how many reactants are there here? At least two. How many reactants are there here? One. That's kind of a giveaway, isn't it? you have one of these and you usually heat it. Or you do something, electrolysis, you try to do something. And so that's kind of a giveaway about decomposition. Now we get into single and double replacement. And we talked about this, and we'll do it again. If ionic compounds are written metal and then nonmetal, if A kicks out B, chances are A was probably a metal, wasn't it? What if A were to kick out C and form the compound Ba and kick out C? Are you with me with this? Okay, so that would be a nonmetal, wouldn't it? So you could actually have single replacement that looks a little different depending on whether it's a metal or nonmetal. I want to show you something that I did not show you in the 10th grade. I thought that was maybe a little bit, certainly too much. And I don't know if I want you to be aware of it. Am I going to actually use it? Here it is. Okay, even though in the 10th grade you would have said, well, I kick you out, and I kick you out. And so you can write it on paper. You're going to find that out also. You can write an equation on paper, but does that mean it's going to happen? It doesn't. And so we can do that. We can practice balancing equations, but chemistry is a little more involved than that. There's a class called, when you get into thermodynamics, some of you are going to eat that up. You're going to love it because they get into the mathematics of compounds and says, thermodynamics says, they tend to favor the lowest energy situation. Why does chemistry happen? Because you have these things that have some kind of a higher energy component to it, and it tends to want to become a more stable thing. That's really what chemistry is. On the other hand, like photosynthesis, you actually build something up. You may be becoming less stable. Well, that's because you had an input of energy. One of the thermodynamic laws says if you leave these things alone, they tend to become more disordered. And that's like decomposition. So if you leave things alone, they decompose. But what if you were to add energy to the system, you could actually build things up. That's what we do. We tend to like to build things up. We build a house, right? But what if you leave it alone for 100 years? Does it build itself up? It doesn't. So anyway, I want to show this to you because I don't know if I want you to be aware of it. I may not stress it so much in my class, but when you say a metal is going to kick out a metal, anybody? And this is called an activity series. The activity series says, and when you see this, and I don't think your book has it. I'm not sure your book has it. I don't think so. It may be in another chapter. But if you're above me on the activity series, you can kick me out. Now, lithium can kick potassium out, but potassium cannot kick lithium out. See that? And this is called an activity series. Now I'll show you something else. If we go down here a little lower, notice that hydrogen's right here. So guess what these guys can do if you put them even in cold water. If you even put them in cold water, they're above hydrogen, aren't they? But even in cold water, all of these can replace H and kick H out and have a violent reaction and make it. They'll make a hydroxide. I'm looking at your faces. All right, everybody get that? All of these are above hydrogen, and these, even in cold water, I'll react with water. What about these guys? Well, if you put me in cold water, a piece of magnesium, nothing's gonna happen. But if that water is pretty energetic, like steam, then I can kick the hydrogen out. I can react with steam, but not cold water. I put zinc in water all the time. Nothing happens. But if I were to put it with steam, I would get a reaction. These, they do not react with water, but if you put these with acids, and all these are the same with acids, all these can kick hydrogen out in an acid. So if I add acid to lead can kick the H out. All right, anyway, and then these, not very reactive. See that? Who's going to kick out? Almost nobody. So gold's not really going to kick anybody out. Now look up here, and I like this one because it's just like the periodic table. Who's the most active of the halogens? Of all the nonmetals, fluorine can kick chlorine out, but chlorine can't kick fluorine out. So if you had sodium fluoride and you combine it with chlorine gas, no, can't kick it out. Now, again, I don't want to stress this. I just want you to be aware of it. If you do go to school and you become a chemistry major, you at least have been aware of it, okay? I may not stress it in this chapter. There's so much stuff in this chapter anyway. But I want you to say, at least I've heard about that activity series thing. Okay. Well, and then we get to double replacement. And, well, here's single replacement. Double replacement. Notice that we have to have, this is probably an ionic compound, another ionic compound, and we have like AB plus CD. Now, the positive part, if this is an ionic compound, this is the positive part, and this is the negative part, right? This is the positive part, negative part. The positive part is going to kick the other positive part, and I'm going to kick you out too. So in double replacement, you can have that. Now later, you'll find out, I'll remind you about double replacement. Many times when you start with two things, what does AQ mean? Remember that? What does that mean? It's dissolved in water. So if I looked at this solution, it would look like water. This one look like water too. See that? So I would put these two things that look like water together, and then, and we'll do this in another chapter, one of the products happens to be insoluble. These are both soluble, so you won't see you. And then right here, they have this thing that doesn't dissolve in water. Matter of fact, it forms a precipitate. Do you remember precipitation reactions? And we'll be using that chart over there. Remember, I don't know if you remember that chart about solubilities. And so the thermodynamics of this would be that this right here is more stable than if it was in an ion form. And then this is aqueous here. So anyway, you'll find out later that double replacements, the driving force is the formation of a solid. Another double replacement might be the formation of a gas. That's one of those thermodynamic things again. Anyway, and then the other one is acids and bases. Look at this acid, and this is a base. Everybody get that? Metal hydroxides. If you have an acid and a base, you always get some kind of an ionic compound called a salt and water. Now, I'm not here to have you memorize this whole page. We're not doing that right now. And then the last one, I think the hardest one, and there are definitely more than 5 kinds of reactions. This is what most reactions fall into one of these 5 categories. When you burn something in chemistry, it means you combine it with oxygen. So if you burn it, you're combining it with oxygen. But I can burn a piece of metal. I can actually burn it. But it's not combustion, Combustion is when it has at least carbon and hydrogen in it. It can have carbon, hydrogen, and oxygen, but it has at least carbon and hydrogen in it. And if you burn this kind of a reactant, then you get what they call a combustion reaction, and you get CO2 and water, like that. Right now, the food that you ate today or last night, it's being ground up, like little smaller particles, and then some enzymes are tearing it up into smaller pieces, and then eventually some of the molecules like sugars will get into your cells, and then another kind of a breakdown will occur in the mitochondria, and so we have that's how you guys get energy. And when they break down the sugar, they said, I can't release all of the energy like burning a piece of paper. God was pretty smart. He said, I need combustion to take place, but I can't have it take place like burning a piece of paper or gasoline, because that would kill the cell. So therefore, I'm going to have some enzymes that are going to slowly, not real slowly, but they're going to take it apart a little bit at a time. And as a matter of fact, some of the energy, I'm going to store it. I'm going to restore it in ATPs. Do you remember anything on biology? So ATPs is how I restore the energy, and I'll use it later, like that. And that's kind of a combustion reaction. And so right now, I'm giving off a lot of CO2 and H2O. That is what I'm doing. And if it's wintertime, you can actually see the H2O. I'd have to go to another planet to see the carbon dioxide frozen at minus 110 Fahrenheit. I could be breathing out dry ice, because that's what dry ice is, frozen carbon dioxide. Okay, you ready? Okay, this? Yes?
Remember yesterday I was talking about with single replacement, like the non-metal, if there could be like non-metal to non-metals. Is that what D is for single replacement?
This one?
Yeah, well, D, like the letter.
Oh, yeah. Halide, the halogens, remember the halogens are in a compound. It's not chlorine, it's chloride. So they call it the halide. And that's the halogen. That's going to be the non-metal and a non-metal. Yeah, good question. Very good question.
For combustion reaction, it says that water becomes, or it's a liquid. Why would that not form into steam or anything? Like, why does that become a liquid?
That's a good question. If I were to burn a piece if I burn some gasoline, there's so much heat there, I don't believe that the liquid would stay, it wouldn't be liquid water. There'd be too much heat there. The water would be in the form of steam.
Okay. Just this specific-
Now, it does say liquid there. I agree. I didn't write that, but
Maybe just a specific scenario.
I suppose that's a good question. Like, what's coming out of my mouth right now? It's vaporized water, but as soon as it hits a cooler temperature, it turns into little droplets of water, liquid water. That's a great question. I think this could be, you could say gas there. That's very possible. Most combustion reactions have enough heat that's going to do that. So let's turn the page. I think you're done with that page. Now, I didn't used to give that page. This is the one I gave before, except somebody typed it for me. That was nice. And so here are the 5 types again. And so now what we're going to do is we're going to classify and learn how to balance again. So let's take a look at the first one. And if you had to put this into a category, take a look at these 5 up here and say what category. And Gabby, if you'll start out, look at the first one. Do you think it reminds you of any of these up here? And one thing I had to teach you, and I know you're in a second year of chemistry, but I have to teach this to you. When you see something like this, you must think of the polyatomic ion as that. You see that? And then you have this. And so here's this and here's that. You see that? This is an ionic compound, isn't it? You have to think that's AB, isn't it? That's AB. All right, Gabby, what do you think?
Double replacement?
Yes. Now, if we take a look at this is AB, and this would be CD. And so if it is going to kick somebody out, silver is going to kick potassium out, but you said double replacement, so potassium is going to kick silver out. And so we go over here, and we get silver chloride and potassium nitrate. Now, I'm not trying to mislead anybody. It is a coincidence. It is a coincidence that it looked like I just cut and paste this. See that? It's just a coincidence that I happen to be -1, I happen to be -1. You do not cut and paste in double replacement. You say this, Potassium will now form a compound with nitrate. And then you do it the way you did last chapter. It is just a coincidence that's a 1-to-1 this time. What if this had been barium chloride? What if it had been barium chloride there? What if the barium formed a compound with nitrate? What would that have been? And I know it, everybody would be a chemist if it was just like that. Everybody would be a chemist. Yeah, barium nitrate. Wait, nitrate's -1 and barium's +2. What are you going to do here? See that? So it's not cut and paste. It just says, I'm going to form a compound with nitrate. I'm going to form a compound with chlorine. All right, so you said double replacement. That's correct. Now, what we're going to do is, this one, unfortunately, when you try to balance an equation, you look for coefficients. Let's take a look. And I noticed on the left side of the arrow, these are called reactants. These are called what? These are called reactants. What are these called? Product. Okay, so reactants, the things that are going to react. And what are the things that are going to be produced? Products. Okay, so when you read a question in this chapter and they said, what products are formed? You look over here. What reactants are, see? Everybody get that? Next. As I scan through here, I say, the arrow says, we haven't reacted yet. On the other side of the arrow, oh yeah, we reacted, see? Before, after. When I started, I had 1 silver. Over here, after I had 1 silver. I had 1 nitrate, see? 1 nitrate, what? 1 nitrate. 1 potassium, 1 chlorine, 1 chlorine. So, I do actually make you, sorry, mean teacher. If you don't have to change, if you don't have to add any coefficients, and by the way, there are coefficients, don't tell anybody, there's a 1 there, but they're never going to write it, isn't it? Same thing with math. When they say x, did you know there's a 1? That's 1x. Okay. Wait. There are coefficients, but if all the coefficients are 1, I want to have you write the word balance because otherwise I can't tell on a test, did you just skip that one? Or did you say, no, I looked at it, it's balanced. Say, I'm going to make you do that. Sorry. All right, let's do the next one now. Let's go down the row. Okay, go ahead, and you're going to do number 2. And what you're going to do is I'm going to tell you, all right, I'm going to tell you this double replacement. So what are you going to write over here?
Did you write H2O plus?
Okay, and
NaCl
HOH is also known as H2O.
plus NaCl.
Okay. And as a matter of fact, this is a classic acid-base neutralization reaction. If you take a look, this is an acid, right? And this is a base. You always get water and you get some kind of a salt. It just happened to be that this salt is the world's most famous salt. Okay? Now let's balance it. All right, what do you think about balancing? So you have on the left side, you have like 1 sodium and 1 sodium. And how about here? 1 chlorine, 1 chlorine. You have 2 hydrogens actually, don't you? So 2 hydrogens and then 1 oxygen. So
It's already balanced.
it is. Okay, so now what I thought I'd do is let's talk about some tricks. I have about 4 or 5 balancing tricks, and that'll help you a little bit. Look at the next one. The next one, what would you say? How would you classify it? Then we'll balance it.
Oh, synthesis.
Okay, synthesis, and we have A plus B yields AB. Now here's trick number 1. Trick number 1 is called the odd-even trick, and if I scan this, I see that this says O2, and I come over here and it says O3. You're never going to get an odd number to equal or balance out with an even number. You get that? It's not going to happen. So what we do is, what's the smallest number that both of these go into? Is 6. Isn't that right? So we have 3 times 2 is 6, and 2 times 3 is 6. Now remember, This right here distributes over everything. So it's 2 times 3, that's 6 oxygens, 6 oxygens. How many ions though? 4. So I got to put a 4 here. Now, once you get in the habit, is when you, because this is trial and error, you always want to go back and see if it can be reduced. If every single coefficient can be divided out by another number, you have to do it. Can this one be reduced? Okay, so that means I'm done. We classified it. Trick number 1, odd even. Okay, let's go to another trick. Here's one. Let's do number 6. Do number 6, another synthesis reaction. And go ahead and balance that one. Scan, scan, scan. Do you see an odd even imbalance? Okay. And what number is the smallest number they both go into? Okay, so we see a 2 here, we see a 5 here, 10, 2 times 5 is 10, 5 times 2 is 10. Now we go back, how many phosphorus do we have? 4. Now wait now, don't say you're done yet. Can you reduce this? No, so we're done. Let's go to trick number 2. Trick number 2. Now, I didn't say you should always write water as HOH, but here's what happens. If I scan this and I notice there's a hydroxide on one side of the arrow and a water on the other side of the arrow, it would actually help you quite a bit to write as HOH. I'll show you why. If I ask you to classify that, you might have a little trouble the way it's written. But what if I write this as HOH? Can you see what's going on? All right, Caroline. How about number 8? If you write this as HOH, what kind of reaction do you think this is? All right, so sodium's going to kick out who? He's going to kick out that H, isn't he? And he's going to form a compound with OH. And here's the H that got kicked out. Now, I know you're saying, oh, there's 2 of those there. I get it. That's true. We're going to fix that when we balance it. All right, let's take a look at balancing it. Also, I think if you have OH on one side and you write HOH for water, watch how easy it is to balance. 1 sodium, 1 sodium. 1 hydrogen that's not in a hydroxide. 2 hydrogens that are not in a hydroxide. So I have to fix that, don't I? Now, how many hydroxides do I have? How many hydroxides? 2, only 1 here. See that? So, one more time. If you see hydroxide on one side and water on the other, if you were to write the water as HOH, it probably will help you. Yes? Yeah. You okay on that? All right. We also have to know, let's see. Let's do trick number 3. What's another one? Oh, I know. That'll be on another page. I would say that I'd like you to do this one right here. Try to do this one. And, yeah, try to do that one and see what happens. How are you supposed to know how to do number 7? They didn't tell me what kind it was. They didn't even tell me the products. So, what do you think? Sitlal, it's your turn. I'm going around the room here. Do you know how to classify this one?
I would say it's single replacement.
It could be. It could be, but usually, so you think the O is going to kick out the H. That's a possibility. I will give you a little hint that when you combine things with oxygen, a lot of times I like to use the word burning. So something's going to get burned here. What is it? It is. Because combustion says, first of all, you're going to burn it. 2, you have at least carbon and hydrogen in the fuel. And then what are you going to get over here is your products? CO2 and H2O. And again, I'd write H2O as H2O here. I did not have a hydroxide on one side. I just keep it like that. Now, this is trick number 3. I could sit here and you could go back and forth and try. You can try it. You want to go ahead and try it? Go ahead and try to balance it, see what happens. So wait a minute. I thought balancing was kind of chump change. combustion reactions, some can be easy to balance, and some can be difficult. So let me show you how to fix some of these. As I scan through here, I knew it was combustion, but I want to show you something real quickly. If you think about numbers here, no matter what coefficient you put in front of there, aren't you always going to get an even number of oxygens? Anything times 2 is even. Now look over here. Anything I put in front of here will give me even number of oxygens. That looks good. I like that. But what if I put what if I put even here? What's even number of oxygens plus even? That's even. That's good. What if you put an odd number here? Odd number of oxygens plus even. What's odd plus even? Any two numbers. That's odd. It will never balance that. Don't put an odd number in front of the water. So what we do here is say, but look, 18, 9 times 8, don't do it. Don't put a 9 there. You'll never balance it. You'll never balance it. So what's the trick? What is it?
You double the.
You double that. So let's try that. Let's put an 18 there, okay? If you double that, now you have a chance to get it right. So now, ready? 2 times 18 is 36 hydrogens. I need 36 hydrogens. There you go. There's 36. But that gives me how many carbons? 16?
32.
Wait, let's say, all right,
No, it's 36.
that's 36.
Yeah.
Yeah, 36 and 36. Now, how many carbons do I have? 16? Okay, now, let's try oxygens. What's 2 times 16? 32 oxygens. What's 18 times 1 oxygen? So how many total oxygens are on this side? 50. Something times 2 gives you 50. Combustions that, if the combustion reaction tries to make you put an odd number there, you're not going to be able to balance it. So you double it. Next, if there is one that's going to have really big numbers, it's going to be a combustion. Some combustions are easy. Most time when you balance an equation, I think 6 would be one of the highest numbers you get unless it's a combustion. You get it? You shouldn't be using numbers like 5 or 11, not unless it's some kind of combustion. Okay on those? All right. Anyway, let's try, everybody try this one up here. Let's try that guy right there. Try number 4. All right, what do you think? So it is a type of combustion, and we should get carbon dioxide and water. So how do we do that? Let's see here. Looks like they want to have 12 hydrogens, so I'll try to put a 6 here. I might have to change it. And then I might have, that gives me 6 carbons. Let's see. And then I have 6 times 2, that's 12 oxygens. Plus 6, 18 oxygens. Is that what I have? So now I gotta go make 18. Now, I already have 6 of the 18 here, don't I? So I need 12 more. So what do you think? Now, can you reduce that? No, almost. There was a 1 there, wasn't there? Okay, you can't reduce it. By the way, in biology, that's the equation for cellular respiration. And aerobic, meaning you have oxygen there. Okay, this is a simple one. If you want to do it, it's single replacement. That should be a simple one to balance. And here's number 10. So the next thing you need to know about balancing equations are God he has these elements here. That's nice. And he has all kinds of compounds. That's really good. I wouldn't be talking to you if he didn't have all kinds of compounds. Anyway, but there are some elements up there that exist differently. For example, you could have something like this. O3 is called ozone, and it's like, wow, 3 oxygen atoms that form a compound? That's pretty weird. Well, we even have this. There's a sulfur 8, octatomic. And those are kind of rare, but the ones that are not rare are the elements that are up there that on this planet, I didn't do it, certain elements don't exist as an element unless it's diatomic. You already know that mercury 1 exists diatomic. So what are the diatomic elements? It's all the ones that end in gin and all the ones that end in ene. So let's look up on the periodic table. And if I said, here's a balloon full of hydrogen gas, hydrogen, what's actually in there? Not that, but 2 hydrogens combined, isn't it? It's a diatomic element. Isn't that right? Now, I never said that you couldn't have 6 hydrogens. I can have 12 hydrogens in a compound, but if it's just hydrogen, if it's just the element hydrogen, it's going to be diatomic. What's the other one? What's the other gen? The other element ends in gen, oxygen, and nitrogen. What I'm breathing right here is almost 80% N2, and it's about 20% O2. That's what I'm breathing right now. I use about 4% of the oxygen and breathe back out some oxygen. 80% of the nitrogen comes in, 80% of the nitrogen comes out. I don't do anything with it. Okay, what are the ene elements? And the good news for you, they're in the same column on the periodic table, aren't they? Fluorine, chlorine, bromine, iodine, and even though we don't talk about acetine very often, the elements up here that even hydrogen has one of its isotopes is radioactive, right? But if you start getting past 83 or higher, every isotope of those elements is radioactive. So what's the chance of a chemistry class using radioactive acetine? They're not. So you don't really read about acetine very often. See that? So these are probably the ones that you're going to be looking at right here. Now, when I say that, because look at number 10. Write this one out. See, I'm going to give it to you in English, and you have to translate it into Cheminese. I made that up. But you have to translate English into Cheminese. So let's try it. Hydrogen gas reacts with oxygen gas to produce water. So what do we have to do here? You have to remember that these elements are diatomic elements, aren't they? Now, by the way, you could do that if you were to put some hydrogen gas in a container and put some oxygen gas in a container. You could shake it all day and nothing will happen. But if you happen to use a little bit of electrical spark, any kind of electricity, you will have a violent reaction. It will violently, and you can look it up on YouTube if you want. I don't do this in class. It is kind of dangerous. I'd have to ask the school, say, school, buy me some pure hydrogen gas. Now buy me some pure oxygen gas, and I'll put it in a container, and I'll spark it. Boom! Okay, first of all, I'm probably not going to do that. I'd have to do it outdoors. But anyway, now, so there's my thing, but now I have to balance this, don't I? Go ahead and balance this one. But if you don't watch it on YouTube, you'll see how violent it is. It will form water violently. That's another thing I think about biology. I think, wait a minute, what do plants do all day? Plants take carbon dioxide and water and make glucose, don't they? And they also make oxygen gas. Well, that's just the part where they make fuel. They're living cells, aren't they? Don't they also have to burn fuel? They do. And so what are they doing? And so I think about that. Plants can do, how do they do that? How do plants take water apart? You can take water apart and you can form water? I didn't hear big booms. And again, that's where enzymes come in and God is pretty smart. I don't want combustion to take place quickly, and I don't want this to take place quickly. All right, everybody know how to balance these in? Are you ready? 2, 1, 2. 2 oxygens, 2 oxygens. 4 hydrogens, 4. Reduce, can it reduce? Okay. All right, let's go on. All right, I'm gonna walk around, and what I'd like you to do is, I did have another trick for you. Here's another trick. Look at number 7. That's gonna be the hardest one on here. As I scan this, first of all, there's only one reactant, so it has to be decomposition, doesn't it? But look at this right here. See this? What element are you not going to try to balance first?
Oxygen.
Oxygen. When you find oxygen in many, many compounds, don't try to balance oxygen first. All right? Save that till later. That's another trick for you. All right, I'm going to walk around the room, and I'm going to stop the video, and what they're doing is they're going to practice this for the rest of the period.